So where we left off at the very end of class last time is we were doing interest problems. And I gave you an interest formula that looked like this. And then one of the last things I told you, and I know we got a little bit into an example at the end of class last time, but the last thing I told you was this interest formula right here that we use for compound interest, there is one time when we don't use this particular interest formula, and we use this interest formula instead. And the big secret to when you use this new interest formula, which some people call the Pert Formula, is when you see the word or the words compounded continuously. And when you see compounded continuously, as opposed to compounded yearly, or compounded monthly, or compounded daily or quarterly, that's when you use this new formula, this, what some people, as I said, call the Pert Formula. And it's got that new number in it that we learned about last time, e, which is an irrational number, so we can't say the decimal exactly, but we do know that it's about 2.718. So this formula right here is the formula that we use for a compound interest problem where they tell us the interest is compounded continuously. So our two formulas, and both of these are given on the test, so you don't need to memorize either of the formulas. You just need to learn how to use them. Both of these are for compound interest. And if they tell you how often interest is compounded with a word, quarterly, monthly, semi-annually, yearly, daily, something like that, then you use this formula. And if they tell you continuously, then you use this formula right here. That's it. So it might seem kind of like bizarre that there's only one time we use this formula, but that is the case. So what I'm going to do, everyone, because I kind of rushed through it last time, is I'm just going to restart the example we were doing at the end of class last time. Does that sound okay to everyone? Just kind of pick that up. So what we have is we had $4,000 is invested at 3% interest, compounded continuously for 20 years. And so as soon as we see this word continuously, that's what tips us off that we're using this formula. That's the only thing I look for to know that I'm using that formula instead of the other interest formula. That word continuously. And so everyone, if we're going to set this up, what's our P going to be? 4,000. And then some people ask, what's the E going to be? But we need to remember that E isn't going to be anything except for E, because E is a constant. E is approximately equal to 2.718, and we'll let the calculator take care of that, but we just put it in here as E. We don't put the decimal approximation in. Our interest rate, just like before, we need to put in as a decimal, not as a percent. So what's our interest rate going to be? What's our R going to be? 0.03 or 0.03. And then this one tells us that we've got 20 years. So depending on the type of calculator you have, you might need to figure out the power first and then take e to that power. Or sometimes if you have the right kind of calculator, you can actually do this all in one go, where you do something like this. Put a little X there, I mean multiplication. But if you don't have that type of calculator, some of the older scientific calculators, what you have to do is you have to do the 0.03 times the 20, get an answer for that, then do e to that power, then multiply by 4,000. Either way, what order of operations dictates on this problem is the last thing you're doing is multiplying by 4,000. So if you have a problem putting this into your calculator, either Rachel or I or any of my SIs will be happy to help you. Actually, pretty much anyone who's taken college algebra before and knows how to use a scientific calculator can show you how to do this on yours. But I'm happy to help. You should get an answer somewhere in the 7,000s if you do this correctly. Does anyone have it for me? And I got 0.48 when I rounded to the nearest two decimal places. Okay, cool. Yeah, and we rounded two decimal places because it's a money problem, so we rounded the nearest penny just like we did with the other interest problems. So when you're trying this on your calculator later, you're trying on it now, if you can't get this answer, talk to Rachel or I as soon as possible, and we'll show you exactly how to punch this in your calculator. Sometimes it's just a matter of pushing two buttons in the wrong order that makes this mess up on you. And that's how we do interest problems. So you'll see a couple of these when you do your homework. And just remember, there's two formulas you use. You almost always use this one unless you see what word? continuous, and then you use this one down here. Okay, cool. All right, so that's it for interest problems. We still got a little bit more to do in 4.2, but I do want to make an observation. And this is an observation I've actually heard some of you make already, just from rumblings and talking, so that's this. Exponential functions, as we discussed last time, come in two basic shapes. We either have the shape that looks like this, and this is what happened when the base was bigger than 1, or we have a shape that looks like this. So this is what happened when the base was between 0 and 1. We get to call these exponential functions because they clearly pass the vertical line test. They're functions, they pass the vertical line test. But what's the other test they both pass? Horizontal line test. And what does that mean?
That means when you invert it, it's still a function.
You still have a function. That's great. So both pass horizontal line test. So inverse, which always exists, but the inverse is a function, and that doesn't always happen. And I'll tell you, I actually, even though I don't really know the inverse yet, and we haven't really talked about what the inverse is yet, I actually already know what it looks like. Because I know that when you do an inverse, you reflect over the line y equals x. So I actually already know what the inverse kind of looks like. It looks like this. Does that look like a reflection over the line y equals x? So whatever the inverse is, which we'll actually learn about today, looks like that. This one over here is a little bit sloppier looking, and the reason it's a little bit sloppier looking is because the function crosses that line y equals x. That doesn't mean we can't draw the inverse. Oops, that's not it. It doesn't mean we can't draw the inverse. It means it's just a little trickier to draw. That one takes a little bit more practice. But either way, when you look at them, I know that one on the right is kind of nasty, but does everyone see how that is a reflection indeed over the line y equals x? It's just that you have some parts on one side and some parts on the other. So the cool thing is, before we even know what the equation is, we actually know, because these pass the horizontal line test, that they have an inverse function. We can actually see what the graphs look like. We can see the inverse functions for these exponentials. Turns out it's going to take us a little while, though, to get to where we know the equation of those. And I'm not telling you you've never seen the equation before, but I will tell you we've never seen it in this class before. All right. So the inverse of exponentials is the main topic in sections 4.3 and 4.4. But in 4.2, we will use the idea that exponentials are one-to-one. So we're going to talk about the inverse of exponentials today in this class, and we're going to talk about that in sections 4.3 and 4.4. But in 4.2, which we still need to finish up here today, we do need the idea that these are one-to-one functions. And I'll show you why. Let's go take a journey back in time. Do you need to do any complicated math to solve for x in that problem, or can you just look at it and solve for x? What do you think? This is not having to do with exponentials or anything right now. This is just me asking you to solve for x. And do you need to do any weird math on your paper for this one? No, why not? What's the answer? 291. How do you know it's 291 so quickly? Because we're adding the same number on both sides. We're adding 4,768 on both sides, and if we're adding that exact same number on both sides, we know how quickly we could just subtract that number from both sides. Everyone agree with that? No big deal there. So, how about this one? x over 719 equals negative 13 over 719. Is that one just as easy to solve? Yeah, that's x equals negative 13. All right, now stay with me. What's x equal? Take a guess. 5. It's going to be 5. Why? Listen to this, everyone. 4 to the x is the same as 4 to the 5. So what does x have to be for this to be a true statement? It's got to be 5. And the reason we can get that one quickly is because the bases match. There's actually a rule that says this. If the bases match, the powers match. In other words, if you know you have b to the n equals b to the m, that actually implies, and it goes both ways, that m and n are equal. I don't know why I switched the order there, sorry. N equals m. You can take that to the bank, everyone. But the reason that works for us, is because exponentials are 1 to 1. That's the reason this works. Can someone give me an example of a function we know really well in this class that's not 1 to 1? Y equals x squared. Really good, yeah. That's not 1 to 1. Now watch this, everyone. Is this a true statement? Is that a true statement? Yes. Yeah, negative 3 squared is the same as 3 squared. That works because I use the parentheses. Does that imply that 3 and negative 3 are the same number? Think about this, everyone. Just because you square them and get the same result doesn't mean that they're the same number. This is absolutely 100% not true. And the reason that's not true is because it's not 1 to 1. There's 2 different x values that give the same y value. But here, there's no way that if these are equal, the n and m can be different because exponentials are 1 to 1. So that's sometimes a rule that people just kind of let slip by and they don't really think about it. But the reason we're allowed to say this is not because you can always say things like this. You can only say that because exponentials are 1 to 1 functions. So what's the punchline? What do I want you to walk away from with this? I want you to walk away that if you know you have a base with a power, and that equals the same base with a power, then that means the powers are equal. But if someone asks you why that's okay, you can say, because exponentials are 1 to 1. That's why that's okay to say that. Because it doesn't work with things like the squaring function, because it's not 1 to 1. Once again, I've made this confusing unintentionally. Doesn't really matter because it still doesn't work, but. Okay, so we're going to use this to do something that we've been doing for years. Solve for x. This has been haunting you ever since you started algebra, and we're going to use this right now. But don't let this spook you. Once you get the hang of this, it is almost as quick as you want it to be. For instance, 1.63528 to the x equals 1.63528 to the 14. What does x equal, everyone? 14, just like that. I don't care how nasty the base is. E to the negative 12 equals e to the x. What's x going to be, everyone? Negative 12, just like that. 3 to the x equals 4 to the 12. What's x?
Well, oh no.
Be silent, you should. I don't know what it is. Why don't I know?
Because the bases are the same.
Bases don't match. So I don't know what that is. Will we know how to solve a problem like that later? Yeah, I'll teach you how to solve a problem like that, but we can't do it this way. Can't do that now. What kind of curveball are they going to throw you on this? Well, they're going to make it so you have more steps to do. This is how they give you more steps to do. They say something like this. 10 to the x plus 3 equals 10 to the 2x minus 9. Now, we know that the powers have to be equal to each other because the bases are equal to each other. So our first step on this is to just set the powers equal to each other. So if we know this is true, then we know this is true, that the two powers have to be equal. And then we just have to do a little bit of old school algebra. Subtract an x from both sides. Add a 9 to both sides. And we get x equals 12. The problem on the right there is just like what we've been doing when you first learned how to solve for x. This is like a beginning solving for x problem. In this class, what did we learn? We learned if those are both the powers on the same base, then we can rewrite it like that. Comments, questions on that so far? Can I make it harder? Of course I can make it harder. I can do this. Go down here. Do the bases match, everyone? Do they match exactly?
No.
No, they don't. But can you make the bases match?
Yes.
Yeah, it turns out if the bases are just same base to different powers, they can be made to match. And what it actually turns out, everyone, is it's easier to make a larger base smaller. So, is there a way to write 25 as 5 to a power?
Yeah.
5 squared. So, this is true, everyone, but see if you are okay with this. Is 25 the same thing as 5 squared, everyone? Can we do that?
Yes.
Yeah, we can. Now do the bases sort of look like they match? Yeah, they do. We just need to remember some of our exponential rules. And these are the kind of rules that we don't always remember. I know I don't, unless I think about them all the time. And that is, if you have something to a power in parentheses, then you have a power in those parentheses, what you do is you multiply the powers together. And if either of the powers has multiple terms, then you do have to distribute. So b to the n to the mth power is b to the nm, and b to the n power with an n plus p on the outside, you have to distribute that n to both of those. So this side stays as 5 to the 3x. This side becomes 5 to the what? 2x plus 14. Do we have an exact base match now? And if we have an exact base match, our next step is to just set the two exponents equal to each other. Subtract 2x from both sides. And we win. Yeah?
So we multiply 2 times 7? So
Yes, we have to. So what this does is it does that, and that's exactly what this rule right here is telling us, that we have to distribute it. Yeah, and it's easy to forget that rule. That's a rule that we probably all learned in one other old algebra class, but we forgot it because we don't use it very often, but that is a rule. That does work. And we've got our answer. And this gets tricky on some problems, absolutely, because sometimes we reduce both bases to a common base. Like on this one right here. See, those bases don't match. And while there is a way to write 16 to a power and have it equal 64, the easiest thing to do in this is reduce both bases down. Now, can anyone think of a good base to reduce both these down to? 4 would work. Was there another one that would work also, but we don't have to? We could do 2 or 4. Either one would work. The secret is you need to know how to rewrite 16 as 4 to a power and how to write 64 as 4 to a power. So over here we do a little thinking. And what power would you put on 4 to get 16? You'd square it. And what power would you put on 4 to get 64? You'd cube it. So we got 4 squared x, 4 cubed, 2x plus 4. And the biggest mistake I see on these problems looks like this. That's the biggest mistake I see people make. What did I do wrong?
You didn't distribute to the 4.
I didn't distribute to the 4. I see this one all the time. I see that one all the time. You got to make sure you distribute when there are those multiple terms. Otherwise, nothing's going to work out nicely. So that's really got to be 6x plus 12 up there, not 6x plus 4. Once the bases match exactly, once they match exactly, and then you just got to remember how to do your old school algebra. I'm going to subtract 6x from both sides. Divide both sides by -4. And I get -3, and I'm done. The negative there doesn't bother me because the exponents are allowed to be negative. Just can't have a negative base. Yeah, we're gonna as we make our way through the different sections of this chapter, we're gonna learn like a new technique to solve for x in every section. So in section 4.2, the technique we learn is having matching bases or making there be matching bases. So the last thing we really have to worry about is what if E starts to confuse us? Because E's brand new to us, so of course E's going to mess with us sometimes. But E is just like any other base. It's a positive number. How can you rewrite that right-hand side? E to what power? E to the, I heard it. I heard someone start to say it. E to the -1. Good. And just like that, because you weren't scared of E, you get something where the bases match. 2x equals -1. 2x equals -1. X equals -1/2. It can almost be said that E is even easier to work with than the other bases because you don't need to bother trying to reduce it down to another base. It's still just going to stay as E. That doesn't mean that it's not irritating to see a problem that looks like this. That looks like the kind we skip and say, I think I'll take a hit on the homework. But we don't have to. A square root is the same as what power? Square root is the same as what power? 1/2. Did I lose someone? I'm sorry. Is there a question?
No, I was just saying I do that all the time.
Do you do this all the time?
Yeah.
Yeah, of course you do. In fact, I probably shouldn't bother teaching because most of you were probably doing this problem on your way to school today. How do I bring that e topside? What do I need to do to the power if I want to bring it up?
Negative.
Make it a negative.
Make the exponent negative.
Make the next exponent negative. Thank you for clarifying. What do I need to make sure I do with that negative 1/2?
Transfer to both 4 and 6.
I have to distribute it? Pain in the neck, but doable. Negative 1/2 is going to be negative 2x plus 3. What's kind of interesting about this problem, everyone, is at any time do we need to know what e was approximately equal to? Do we need to know that e was about 2.7?
No.
We just needed to know it was a valid base. It didn't really matter that it was e. In fact, everyone, well, let me finish this one, then I'll show you. Got ahead of myself there. Just got to make sure I finish up this problem. Subtract 3x from both sides. Subtract 3 from both sides. Divide both sides by negative 5. I get 2/5. But I'll tell you, class, you can't let e spook you. It's not in charge. We are. Because you see that problem right there that we just did with e? Let me show you something. I just rewrote the exact same problem, except instead of writing e, I wrote 5. Everyone agree with that? This is the exact same problem, except I've written 5 instead of e. Does anyone know the answer to this problem?
It's 2/5.
It's still just 2/5? It didn't matter. Don't let e ruin your day. It's our friend. If it's not your friend yet, it will become your friend. One day you'll be telling people how cool e is. Yeah, it didn't matter. It didn't matter that this one had e and that one had 5. All that matters is we would have gone through the same process with 5s as we would have with e's. Why? Because e and 5 are both just numbers. They're both valid bases.
What if they don't match?
If they don't match, then we got to use a different technique that we'll learn in a later section, which can happen. If you can't make them match, so for right now, let me write square root. Right now, I have no way to solve that problem because I can't make the base 3 match the base 5 no matter how hard I try. So right now, I can't do that problem. So right now, what we learned in section 4.2 is just how to solve them when the bases match, or we can make the bases match. And that's frustrating, I know. But we can't solve that type of problem yet, but we'll get there. We'll get there sure enough next week. Are we cool, class? All right, you practice those in the homework. You let me know if there's any snags. And we're going to call section 4.2 done. And the division that the book made in these two sections always seems kind of arbitrary to me, where they kind of break these up. 4.3 and 4.4 are basically both a lot of information about the same topic, so I'm going to kind of do these together. So this is going to be kind of difficult to follow along in your books directly, but just know that when I'm done with all this, we're going to cover what we need to know in 4.3 and 4.4 together. We kind of did this back in our second unit, I think, with sections 3.3 and 3.4. So we're going to kind of group them together, so we will finish them at the same time. So if you do some homework, don't be alarmed if you can do some problems in 4.3 and some problems in 4.4, but not other problems in 4.3 and not other problems in 4.4. And I made a couple pictures ahead of time for this. Because if we're going to do something new, we should talk about what we already know first. Inverses. They undo what the original function did. If the original function turns a into b, then the inverse turns the b back into an a. They undo each other. The domain and range of an inverse are the range and domain. The domain and range of a function are the range and domain of the inverse. They swap with each other. That's all stuff we know. We know how inverses work. If you plug 2 into the original function, that turns it into a -3. If you plug -3 into the inverse, that will turn it back into a 2. That's how inverses work. Inverses do the opposite operation. What's the opposite of adding 5, everyone? Subtracting 5. That's why x plus 5 and x minus 5 are inverses of each other. What's the opposite of dividing by 3? Multiply by 3. That's why x divided by 3 and 3 times x are inverses of each other. What's the opposite of multiplying x by 2, subtracting 5, dividing by 3, and then taking the cube root? Well, you can do that 4-step process we learned last time, and say the opposite of that is cubing x, multiplying it by 3, adding 5, and dividing by 2. You could verify this if you wanted to. But these are all inverses. And we've heard of inverses before, even if maybe you didn't use the word inverse. I mean, we knew that adding and subtracting, multiplying and dividing were the opposites of each other, and they undid what the other one did. And you actually probably first saw inverses a very long time ago. I call this slide Inverses in the Beginning. We were all first starting to feel good about ourselves with math. And they didn't use the word inverse. You see, once upon a time, someone gave you a problem to solve. And they said, what's 3 plus 5? And they give you a little box here or a little blank right here. And you wrote the answer, and you got... Dumb luck that. All right, and you wrote the answer. But then, one of your teachers got really clever and said, you know what, I'm going to ask them this question instead. 3 plus what equals 8? And what they were actually doing is they were actually introducing you to inverses. Because instead of just asking yourself, what do you get when you add 3 and 5, you suddenly had to kind of think backwards. You had to think to yourself, what number did you add to 3 to get 5? Or 8. What number did you add to 3 to get 8? That's great, everyone. Okay. And the number you add to get 8 is 5. Good. Apparently I didn't pay attention way back when. So, inverses are backwards thinking. Did anyone in this room learn division before they learned how to multiply? No, you don't do that. You don't teach someone how to divide before you teach them how to multiply. In fact, multiplication is so important to division that most teachers will teach you the way you check your answer to a division problem is you do a multiplication problem to check it. So, to understand, actually I think this is what it says on my next picture. I just did a few pictures. Don't worry everyone, the rest of the lecture isn't pictures. I just made a few because I thought they were so fun to make. This is the big question for understanding inverses and exponentials. This is the question we need to be able to answer today, everyone. What power did I put on that base to get that result? This is how we're going to understand the backwards form or the inverse form of exponentials. You all know how to do this. What's 3 squared, everyone? 9. Now the question we're going to ask is this. What power did I put on that base to get that result? And the answer is 2. Can we do that, everyone? Can we look at it and think backwards rather than taking a base to a power and getting a result? Can we look at the base and the result and give the power? Because that's what we need to be able to do. If given base and result, we need to give the power. This is how inverses work for exponentials. It's a brand new type of question. What power did I use? What power did I use to get there? What power did I use to get there?
2.
What is it?
2. Negative 2.
Negative 2. I needed the 2 to square it. I need the negative to put it on the bottom.
And do calculation.
So it's going to be negative 2. Yeah. The 2 squares the 5, and the negative puts it on the bottom. All right, try this one. This one's harder, everyone. No one say the answer out loud. I want everyone to have a chance to think about this one. I want everyone to have a chance to think about this one. No one say anything. Everyone just ponder on your own for a moment. And then we'll think about what we have to do. We have to get it down in the bottom. And we don't raise it to a power. It looks like we take the square root of it. So what power is going to put it on the bottom and take the square root? Tell me, please. Negative 1/2. I asked before, did anyone learn division without knowing multiplication first? And the answer is probably no one does that. No one does that. And unfortunately, I know we just started learning about these a couple days ago, but in order to go backwards, you do need to know how to go forwards. In order to understand subtraction, you need to understand addition. In order to understand division, you need to understand multiplication. In order to understand how to go backwards with these things, we need to understand how to go forwards. So this would be very tricky. If you didn't know 9 to the negative 1/2 was 1/3, yes, it's going to be really hard. Just like you're not going to be able to do 12 divided by 4 equals 3 if you don't know that 3 times 4 equals 12. So, let's try this. Actually, let's talk about what I just said. How do you know that? What's the quickest way to explain to someone that that's true? How would you explain that to them?
3 times 4.
You would explain the division using multiplication.
Yeah, 3 times 4.
Yeah, good. Explain your division by using multiplication. You would explain, I know that's true because I know that 3 times 4 equals 12. That's why I know that 12 divided by 3 is 4. So, if someone asked you to explain your answer to this question, how do you know it's a 3 there? You would just repeat back to them what it says. If someone said, how did you know to put a 3 there? You would say, because 4 to the 3rd is 64. You would explain it with an exponential. How is that 3? Because 4 to the 3rd power is 64. All right. Notation is our friend. Notation is our friend. What is the sum when you add the number 3 to the number 7? 10. Now, would you rather see that question on a math test, or would you rather see this question on a math test? 3 plus 7. I think this one better. And I like that better because I'm used to it. I know what it means. I understand the notation. I understand this is the symbol for 3, this is the symbol for 7, this is the symbol for addition, this is asking me what the answer is. I get it. What is the product when you multiply the number 4 by the number 6? 24. We can answer that question, but does that one make just as much sense, if not more sense to us, because we know what that means?
Yeah, so if I put 24, I'm not gonna get like full points.
No, I mean, they both have an answer of 24. They both have an answer of 24. The point I'm trying to make very briefly here, and maybe I'm making it more confusing than it needs to be, is mathematical notation. Sometimes people get very frustrated because they look at all the new symbols in the book, and they're like, I don't even know what this means. The thing is, once you've experienced it, once you've practiced with it, once you've worked with it enough, we actually prefer the notation to all the words. Because now that we are also comfortable with adding and multiplying, we have no problem with this. So since I'm going to introduce a new notation today, I wanted to remind you that notation is actually a good thing. It's just a matter of being used to using that new notation. So, when someone says, what power do you raise the number 2 to get the number 8, they are actually asking this. What power would you put on 2 to get 8? And we can answer that. What is the answer to that? 3. But I can't think of a single college math course that uses the notation of fill in the fun little box. So we're going to need something else, and it's going to look like this. Everyone, that's LOG, the word log, like log cabin or log cabin syrup, or I don't know what else you do with logs. Log ride, Splash Mountain is a log ride at Disneyland. Okay, that's the word log, everyone. And what we're going to do is we're going to put a little subscript down here. That's a little subscript. So it's not on the same level as G, it's hanging out down below. And then we're going to put in a regular 8. That's not a power on 2. If you look at this really quickly, you might think, is he writing 2 to the 8th there? I'm not writing 2 to the 8th. 2's down below, 8's up above.
And do you know how to write 2 down below?
I'll show that on your calculator. I'll show you how to do this later, don't worry.
Okay,
This right here is asking the exact same question as both of these. It is a brand new notation to us called the logarithm. And like any other notation, what we're going to have to do is we're going to have to get used to it. Because rather than me doing this fun little box every time, or me writing out in words every time, we need to write this. Now, it's still okay to think these things to ourselves when we look at this. In fact, I always do. Whenever I look at this, I think to myself, they are asking me what power I would put on 2 to get 8. So what's the answer to this, knowing it's the exact same question as both of these? 3. It's a question we already know how to ask. It's a question that now we know how to answer. We just need to get used to what the people are going to write it like this. We need to get used to the fact that when someone says to this to us, what they're actually asking is they're asking 3 to what power is 9, or they're asking what power do you put on 3 to get 9? All of these are asking for the same thing, but the way we're going to see in college algebra is this new notation called logarithm notation. And what's the answer to this? 2. So can we answer these? We can if we practice and we get used to the new notation of logarithms. How is a logarithm structured? It's structured like this. You write the word log. There's a base down here as a subscript. There was the result. And the answer we put here is the exponent that made it happen. What was the exponent that made us get this result using this base? That's what they're asking. And yes, everyone, this is called the base down here. Look at that 3 down there as the base. Look at it over here as the base. It's still called the base. We can use, I always do that, I always turn my H into an M when I'm writing logarithm. We can use logarithm notation to write a logarithmic function. We can use this logarithm notation to write what we call a logarithmic function, a brand new type of function to us in college algebra, a function we'll learn more about at 11:30. I'll see you then. So I wrote a few things on the board while you were at break, just to kind of summarize what we've learned. A logarithmic function will have a base on it. So when I write a logarithmic function, which I'm about to do, I do have to put a base on it. And I'm using the word base because it's the same rules that we have for exponentials. The base needs to be a number greater than 0, a positive number that's not the number 1. The x values we're going to plug into the logarithmic function are the results of taking that base to different powers. The y values that come out are the powers that made those results happen. That's just a way of putting in words what we're talking about before break. Now, before anyone gets frustrated trying to use their calculator on this, I will tell you that most scientific calculators do have that LOG button on them, which does mean logarithm. The problem is that only means base 10 logarithm. We'll talk about why that is the case in a moment, but for right now, you don't need your calculator for what we're going to be doing. So don't get frustrated trying to do this on a calculator and be getting different answers than me, because that LOG button is not going to work for this example. Here is a logarithmic function. The numbers I put in are going to be the results I get from taking 3 to certain powers. So, for instance, if I ask everyone to plug a 9 in here, what is the answer going to be? 2. Explain how you know it's 2, please.
3 squared is 9.
You justify your answer to the logarithm by using an exponential. You know it was 2 because you knew that 3 squared was 9. What's the answer to this one, class? Someone else. 1. Can you justify that for me? Can you tell me why?
Because 3 to the first power is 3.
Perfect. That's exactly how you know that. Well done. How about this? A little trickier here. Anyone know that one? Someone new?
1 to the 3rd power is still 1.
No?
No.
Close. It's something. It's a rule we learn. You just need to think backwards.
0.
What is it? I heard a mumbling. 0. Why is it 0?
Anything to the 0 power is 1.
Because anything to 0 power, in this case 3, is 1. Now, of course, that's frustrating if you haven't had enough time to absorb exponentials yet. But does everyone agree that that's true, that 3 to the 0 is 1? So therefore, if we take the log base 3 of 1, we get 0. And that is how you'd read that out loud, by the way. This is how you'd read this out loud. You'd say g of 1 is equal to, well, we'll just say equals log base 3 of 1. That's how you'd say it out loud. G of 1 equals log base 3 of 1. All right, can we plug some other numbers in there that would be pretty easy? Can we do this? I wonder if I can do this. Can I do this? 1/3. Is that a fair thing to ask you to do without a calculator or anything like that? What's going to take a 3 and just throw it on the bottom, everyone?
Negative.
-1. And I'm doing the same thing you're doing. I've just been doing it for longer. When I see this, I think to myself, what power did I put on 3 to get 1/3? We all have to think the same thing. It's just that some of us have maybe seen this before. Some of us have gotten a little bit more practice with it. But we can all think the same thing when we do this. What power do I put on 3 to square it and put it on the bottom? Negative 2. Why? Because 3 to the negative 2 is 1/9. Now, class, there are certain things we need to know about these logarithmic functions. First of all, they're not invincible. There's certain things they can't do. For instance, what power do you put on 3 to turn it into a 0? Anyone feeling confused, lost by this question? You should, because we can't do this. If when we plug a number into a function that's impossible to get an answer, what do we know about that number? It's not part of the what? Yeah, if you can't plug it in and get an answer, then this number is not part of the domain. What power would you put on 3 to turn it into a negative 3? Be silent, you should. That question stinks just as much as its friend up there. We can't do either of those things, because negative 3 is not in the domain either. We need to figure out how to figure out the domain of this thing so I can plug numbers into it. This question you can answer, but this one would require technology to answer. So this one is possible once we learn how to use our calculator. That one is possible to do. That one is possible, just we can't do that yet without using a calculator. So, yeah, and you might have a calculator that can do this right now, but some people don't, and I'll teach you more about this one later. We're only going to take logarithms of positive numbers, everyone. And that concept will become more clear to you in a bit, why we only do that. We're only going to take logarithms of positive numbers. Now let me show you something, everyone. Now is time. It's time to do something cool. Here's an exponential from last class. We can put any number we want in there, everyone. What's 3 to the 0? 1. What's 3 to the first? Itself. 3 to the negative 1? 1/3, itself flipped. 3 squared is 9. Negative 2 is itself flipped and squared. Are we okay with this, everyone, from last class? Jog our memories a little bit, but we did do this. Now, here's the function that I was working with on this previous page, right here. Right here, log base 3 of x. Exact same function I was just working with. And I found a bunch of ordered pairs on it by plugging in different numbers. Everyone see this? So, from the last page, some of the numbers that I plugged into this thing were 1/9, 1/3, 1, 3, and 9. And the answers I got out were -2, -1, 0, 1, and 2. What do you see? They're inverses of each other. That's our punchline, everyone. That's our punchline right there. These functions are inverses of each other, everyone. I told you when we started doing this that the exponential has an inverse, but it's not something we've seen in this class before. In Steve's class, college algebra this semester, have we ever talked about logarithms before today? No, I'm not saying none of you have seen logarithms before. Maybe you've seen them before, maybe you've seen them on your calculator, maybe you've talked to a friend, maybe you took college algebra before, I don't know. But it's brand new to us today. This is the way we write the exponential. I think this is my one that's way too big. Oh, that's not so bad. Okay. Here is 3 to the x. Here is log base 3 of x. And what is this right here? What am I drawing now? What is that line right there? It's y equals x. Everyone, I'm going to write this down in a second, but the inverse of an exponential function is a logarithmic function. Why? Because this takes the 3 to a different power. This one says, give us the result, we'll tell you the power that made it happen. They're the opposite questions of each other. The inverse of an exponential function is a logarithmic function with the same base. It's awkward because it's new. You might not have asked this question to yourself before. What power did I put on that base, or what power did I put on this number to get this result? That's a brand new question to some of us. That's why they're new. That's why they're kind of shifty. But that's exactly what's happening here, everyone. It is a reflection. All the ordered pairs are swapped, every single ordered pair. Look at this green one up here, everyone. Look at it. Isn't it beautiful? No, that's not what I want you to look at. I want you to look at its domain. What's the domain look like of that green one right there? Careful, just the green one.
Oh, 1.
0 to
Yeah, the way we do this, remember, is we say it's 0 to infinity, but not quite 0, so we put a parenthesis on there. What's its range? Does it look like it might go up and down forever? It does. Which is the exact opposite or swapped domain and range of the exponential. Did the exponential 3 to the x, does that have an x-intercept? I'm sorry, or a y-intercept? This black one here, does it have an x-intercept or a y-intercept? Has a y-intercept right here. There's a y-intercept of 0, 1. Look at the green one. What does it have? An x-intercept of 1, 0. Why? Because every single ordered pair was flipped. When you write an inverse, what are you doing? You're swapping x and y. So 0, 1 becomes 1, 0. You're swapping x and y. This exponential has a horizontal asymptote of y equals 0. If we swapped x and y, what would that y become? Don't overthink this. If we swapped x and y, what would that y become? It'd become an x. That's why the logarithm one has a vertical asymptote of x equals 0. I hesitate to put it in here. I don't want to make this thing too garbled, but there it is right there. You can see it. These functions are inverses of each other, everyone. And now you can write the inverse of any exponential. We're very good with inverses because we know the opposite of many things. Do we know what the inverse is of x cubed? Just for instance, just to go back in time a little bit. Cube root, it's the opposite. What's the opposite mathematical operation of adding 7? Subtracting 7. There's an exponential. The inverse of every exponential is a logarithm. What's the base on this exponential? 4. Its inverse function, therefore, is log base 4 of x. That is how you write an inverse function for an exponential. Someone give me a positive number not equal to 1. 5, okay. Log base 5 of x. If that's a logarithmic function, what's its inverse? 5 to the x. Is e a valid base? Yeah, it's about 2.7, right? What would the inverse of log base b of x be? E to the x. You got it. This is important. We'll talk more about this later. Some of you might already know something about that right there. You might not like the way I wrote that. If you do, just hold on to that idea for a moment. Everyone else, this is completely cool. This is how you do the inverses. This is how we do inverses. So now it's time to talk about this. So if we don't write a base on a logarithm, then we assume the base is 10. There are some things in math that we do often enough that we don't bother to write the number that we mean. For instance, that's the cube root of 64, everyone, which is 4. That's the square root of 64, which is 8. What's that one?
16.
What's the square root of 64?
Oh wait, that's just 8.
It's just 8. But how do we know that's a square root if I don't write the number up here? It's because we use square roots so often that we don't bother to write the 2 up there. Does everyone agree with that? We know it's there. We just don't bother to write it because it comes up so often. Base 10 logarithms come up so often that we don't bother to always write the 10. So, if someone says you have an exponential 10 to the x, someone might say the inverse of that is log base 10 of x. Someone else might say that the inverse of that is log x, because they know if they don't write that 10 that you're supposed to assume there's a 10 there. What's 10 squared, everyone? 100. What's the log of 100? How do you know it's 2?
Because you can do the square root.
Why do you know that's 2? Like, well, how would you explain that to someone if they said, how do you know that's 2? I'm not talking about this. I'm sorry. What I'm talking about is how do you justify your answer to an exponential or to a logarithm? What do you say?
You would do the exponential.
That's right. You say that log of 100 is 2 because what you know is this really says log base 10 of 100, and you're writing 2, and you know that 10 squared is equal to 100. That's how you know the answer to that is 2. Now, for those of you who want to, you can take out your calculator and take the log of 100 on it. Because that button on your calculator that says LOG that's been waiting for you this whole time, that means log base 10. If you do log of 100 on it, you will get 2. You will get 2. So if you want to experiment with that button on your calculator, do log of 100. If you're getting an error, try typing in the number, then hitting log. But you can take the logs of different numbers and you can see what the answer is. So you can see what that button is for. That is specifically for doing log base 10. The calculator trials. You will also see that on some calculators, if you try to do the log of negative 10, depending on your calculator, that's either going to give you an error or it's going to give you an imaginary number. We don't do it in this class, though, because negative 10 is outside our domain. So some of the more sophisticated calculators do give an imaginary number when you do that. Other ones are just going to shoot out an error at you, because we only take the logarithms of positive numbers. Rachel and I would be happy to help you learn how to use your calculator. If you can't. Someone want to do the logarithm of 816 on their calculator and give me a decimal to 4 places?
.94.
I got 2.9117. What'd you get? Well, now I don't know. Hold on a second.
I got 2.911.
117?
Yeah.
All right. If you're not getting that, show me your calculator later. I'll give you a hand. Everyone, what does that 2.9117 represent? It's not just some horrible decimal on your calculator. What does it actually represent?
It's the exponent.
It's the exponent you would put on what? To get what?
816.
That's great. So 10 to the 2.9117 is approximately equal to 816. Why do I say approximately equal? Because that's a rounded decimal. So that's not going to give you exactly 816. What's the log, which is only spelled with one G, of 1,000? What did we say that was? Log of 1,000? 3. What's the log of 100? 2. Notice that 816 is between 100 and 1,000, and 2.9117 is between 2 and 3. Logarithms actually make sense, everyone. Logarithms actually make sense. If you take the logarithm of a number between 100 and 1,000, you will get an answer between 2 and 3. The more you work with these things, the more sense they make. Trying to tell you everything you need to know about logarithms in an hour and a half is very difficult. You do need to practice them on your own. But they do make sense. All right. I'm going to go out on a limb on here and say there's another base we use a lot, and it's called the natural base, and it's actually the base that you're going to use most often in math. You use it even more than base 10. If you keep going on in math, I promise you this is the base you will use most often when you work with logarithms. Does anyone know what base I might be talking about?
E.
Yeah, it's E. We use E as a base so often that it gets its own notation when we use it in a logarithm. The inverse of an exponential is a logarithm with the exact same base. So the inverse of e to the x is log base e of x. It turns out, everyone, that this is called the natural base. And it is used so often in mathematics, it gets its own notation. Look at your calculator if you have one. Do you see a button near LOG with a little e to the x above it, maybe? Look at your calculator. Look near the LOG button. See if you see another button that has an L on it. What do you see? You should see an LN button. You should see an LN button. E gets used so often as a base that it gets its own notation. If you see ln, that's still a logarithm. It means the exact same thing as this. It just means base e. It comes up so often in mathematics that it gets its own special way of writing it. It gets its own special way of writing it. So, if someone asks you, what is the ln of 14? What they are asking you is they are asking for the decimal approximation of the power you would put on e to get a 14. That's what they're asking you for. If you type ln of 14, what you're doing is you're saying the logarithm base e.
2.63.
2.6391. This is read aloud as ln of x, or some people say ln of x, or some people say natural logarithm of x. But that's an L in front, not a capital I, that is an L. Sometimes people ask me, if it's called a natural logarithm, why is it ln and not nl, or why don't you say logarithm natural? And I tell those people to leave. No, it is a natural base, it is a natural logarithm, but we do write ln. We do write ln. I don't know why people don't say logarithm natural of x, because that certainly seems like it should be. But that means natural logarithm, everyone. The two bases that most calculators can do are log, base 10, and ln. And for right now, we just have to be happy with those two bases. Okay. Logarithms are the inverses of exponentials. What are the two bases we use most often with logarithms? Base 10, base e. That's why if we don't bother to write a base, we assume it's base 10, and that's why base e gets its own notation. All right. Summary and learning about exponentials. Some of this will be summary, some of this will be new. I made some pictures so I wouldn't waste your time by drawing a bunch of graphs today, so I did make some pictures for this. Let's do this one first. Copy. I hope this is the right size. Yeah, that'll work. Everyone, what you see up here is you see a graph of an exponential and you see the graph of a logarithm. Exponentials we learned about last time, logarithms we learned about this time. This is what an exponential graph, this is what a logarithm graph looks like if you are talking about logarithms and exponentials with a base bigger than 1. If you have a base bigger than 1, your exponential looks different than it does if your base is between 0 and 1. If you have a logarithm with a base bigger than 1, it looks different than a logarithm with a base between 0 and 1. Exponential with a base bigger than 1 goes left and right forever, hangs out strictly above the x-axis, has a y-intercept, has a horizontal asymptote, and is increasing. Every exponential function that has a base bigger than 1 has the same basic shape of this. They all have different ordered pairs except for the ordered pair 0, 1, but they all have that same basic shape, whether it's 3 to the x, 7 over 4 to the x, e to the x, or 10 to the x. They all have that same basic shape. Every single exponential function passes the horizontal line test. So therefore, every single exponential function has an inverse function, which is a logarithmic function with the exact same base. And if you sketch a logarithmic function, the domain and range are swapped from the exponential. The y-intercept becomes an x-intercept because every ordered pair is swapped. The horizontal asymptote becomes a vertical asymptote. Over here, what was a horizontal asymptote of y equals 0, here is a vertical asymptote of x equals 0. Over here, what was a y-intercept becomes an x-intercept over here. They are both increasing. That actually kind of blows my mind a little bit when I first heard that. Because it certainly seems like if a function is increasing, its inverse should be doing the opposite. It seems like it should be decreasing. That's just what would make sense in my mind. But apparently I'm wrong. Because if you look at these, are they both going uphill from left to right? Yeah, so that's not a rule. It's very tempting to make up rules that aren't real. And if you want to know the inverse of an exponential, all you have to do is rewrite it as a logarithm with the same base. The inverse of 3 to the x is log base 3 of x. The inverse of 7/4 to the x is log base 7/4 of x. My 4 got chopped off, sorry. The inverse of e to the x is ln of x. It gets that special notation because it's base e. The inverse of 10 to the x is log of x. We don't have to write a base if we assume the base is 10. Well, that's pretty cool. Does that take care of every exponential and every logarithm ever? No, because these are all specifically for base bigger than 1. Are we allowed to have bases that are not bigger than 1? What other kind of bases do we have? Not negative bases, but what do we have? Decimal or between 0 and 1. Class. I'm just going to make this the only thing on that page. That's it. New page. Some exponential functions go downhill like this. Which ones go downhill? The ones where the base is between 0 and 1. Their inverses also go downhill. They're also decreasing. But a lot of things that we would expect to happen with inverses still happen here. Here's a horizontal asymptote of y equals 0. Here's a vertical asymptote of x equals 0. Here's a y-intercept of 0, 1. Here's an x-intercept of 1, 0. Domain, range, they swap. Y-intercept becomes x-intercept, horizontal asymptote becomes a vertical asymptote. They are both decreasing. If you have a base that's between 0 and 1, whether it's an exponential or a logarithm, you're going to have a decreasing graph. The reason these look funny to me and they look funny to a lot of people is we don't see these as often. And the reason we don't see these as often is because what are our two most important bases, everyone? 10 and e. And those are both bigger than 1. So the ones we see most often are these back here, because that's base e or base 10 has that shape. So that's why we don't see this other one as often. It's still out there. But I'd say in general, when you work with mathematics, you're going to see the base 10 and the base e most often, so therefore you're not going to see this one as much, or this one as much. But they're still important. So, class, what we kind of have is we kind of have four new basic functions. We have exponentials that either look like this or like this. And we have logarithms that either look like this or like this. By the way, everyone, real quick here. Does this logarithm graph, which I will call f of x equals log of x, does that look similar to another graph that we learned about in this class to you? What does it look kind of like? Kinda.
X squared, x cubed.
Close. Not x squared, x cubed. What was the other one? Not x squared. Does it look sort of like the square root graph? I'm not saying they're the same graph, but does it look sort of like the square root graph to you?
Yeah.
It does to me too. I think it does look sort of like the square root graph. I'm thinking that if someone said, name a graph that looks kind of like that, I would say, well, it's got some different features on it. It starts in a different place, but I would say those graphs look kind of similar to me. I would say they look kind of similar to me. Can someone go ahead and do the square root of, actually, let's go nuts here. Let's go nuts. Let's do the square root of 1 million. You can actually do this without a calculator if you know how to work with your zeros. Good job, 1,000. Is that an ordered pair that's on this graph, everyone? Is that an ordered pair that's on this graph? This thing grows so slow. Look at this, everyone. You got to go all the way out to 1 million to get up to 1,000. That's a very far way out. Now, let's go ahead and plug 1 million into this one. Now this one you can do on your calculator because I'm asking you to do the log base 10 of 1 million, or maybe you know how to do it without a calculator. 6. This one, you go out to 1 million and you get 6. Do they look kind of similar when you just look at my pictures up there? Yes, they do. This one is growing so much more slowly. If you go up to 1 million on both of them, I realize 1 million is nothing to scoff at. That's way far out there. I'm not going to go out that far. I'm not even like in the parking lot there. I don't even know where I am. What am I in? Estes Park? If I go out to 1 million. And this one does make it all the way up to 1,000. This one only makes it up to 6. It's because these are inverses. This right here has an inverse function of x squared with the restricted domain. X can only be greater than or equal to 0. This one right here has an inverse function of 10 to the x. Now you might remember from our last class, I did something called the illusion of growth on a hand-drawn graph. What grew faster, exponentials or the quadratic x squared? What grows faster? Exponentials grow faster. So, the logarithm grows slowly because the exponential grows so fast. That's why the logarithm grows so much more slowly than the square root function, because the exponential grew faster. So the faster the original one grows, or the inverse grows, then if you look at its inverse, the slower that's going to grow. Now, this is not something I expect everyone to memorize and walk out of here today and tell your friends when you bump into them in alleys, when you're doing your street math. But I do want to make sure that we understand that when I draw a drawing like this, I sketch my logarithms like this, I sketch my square root like this, and you can almost think, oh, those graphs are very similar, they're the same thing. Well, they're not the same thing. They have different ordered pairs on them. They have different domains. This one includes 0, this one does not. They have different ranges. They are different graphs. But the biggest point I was trying to make here is even though these two arcs that I draw make it look like they're growing at the same rate, they're absolutely not. They're both growing slowly, yes. But the logarithm grows so much more slowly. So much more slowly. Okay. Because exponentials and logarithms are inverses of each other when the bases match, they can undo or cancel each other when used in the same expression. And if you don't like that, I'm going to show you exactly what I mean by that. Because exponentials and logarithms are inverses of each other when their bases match, they can undo or cancel each other when they are used in the same expression. Let me give you an example of what I mean by that. 8,647 times 12 divided by 8,647. What's the answer? 12. No big deal. It's 12 because I am multiplying and dividing by the same number, so they cancel each other out, and it's very easy to find the answer. Does everyone agree with that? 16 plus 1,486,219 minus 1,486,219 equals what? 16. Because they cancel each other out, because adding and subtracting with the same number, or multiplying and dividing with the same number, are inverses of each other. This one right here is not as much fun. 1,268 times 4 over 1,269. Is that one that fast to do? No, because even though I'm both multiplying and dividing, am I multiplying and dividing by the same number? No. So this one is not easy. It's not impossible. It's not illegal. It's not the worst thing I've ever seen in my life, but it's not easy to do. But inverses and exponentials and logarithms are inverses of each other. So they will undo each other if you have the same base. Pay close attention to the question I asked you. Does anyone off the top of their head know what 20 to the 13th power is? I don't either. I don't. Okay. I don't know what it is. But let's think about the question this is asking. This is asking, what power do you put on 20 to get 20 to the 13th power? When I write it like that, it should almost seem like a ridiculous question. Hey everyone, what power would I put on 20? What power would I write right up here
50?
so it looks like this? Think about that, everyone. What power would I write right here, in this spot right here, so it looks just like this one? 13. This is asking, what power do you put on 20 to get 20 to the 13th power? What happened, everyone, is we have a base match here. And since the bases match, just like its friends up here, they undo each other. This multiplication and division undid each other. This addition and subtraction undid each other. This logarithm base 20 and this exponential base 20 undo each other. They're inverses, and that's why the answer ends up being 13. And if you understand what this is asking, you pretty much answer the question when you ask it. Listen carefully again. What power do you put on 20 to get 20 to the 13th power? 13?
50?
Yeah. Well, shoot. If I write ln, it's not base 10, what is it? Base e. This is also base e. I've got base e and base e. This is asking this question. Listen carefully, everyone. What power do you put on e so you have e to the 7th power?
7.
7. What power do you put on 10 so you have 10 to the 949th power? 949. What power do you put on 3 so you have 4 to the 8th power? What's the best answer to give here? I don't know. Why don't you know?
Bases don't match.
Bases don't match. That's like this up here. We can't solve this one quickly because I'm not multiplying and dividing by the same number. If the bases don't match, you can't use this cool trick that says that log base b of b to the nth power is n. That they cancel each other out. We can't do that if the bases don't match. But if the bases match, we can go ahead and do that. It's awesome. And it's not supposed to be anything profound. I still got 3 minutes. It's not supposed to be anything amazing. It's just supposed to be, look, these do the opposite. Logarithms and exponentials are inverses of each other. They're the opposite. They undo each other. You put them in the same expression. It's exactly why this happens. Now this, well, let me ask you this. If there was any justice in the world, what do you think that might be? It is 7, and here's why. Log base 5 of 7, which you see right there with the red box around it, represents the nasty decimal power you would put on 5 to get a result of 7. I do not know what log base 5 of 7 is, but I know what it's asking for. I know that this right here is asking for the power you would put on 5 to get 7. That is a really, really ugly decimal. One that I can't even do on my calculator right now because my calculator can only do base 10 and base e. I'll show you how to get around that later, by the way. So I don't know what that number is, but I do know what it represents. It is the power that I would put on 5 to get 7. Now, put that nasty power on 5. And if this represents the power you would put on 5 to get 7, and you put it on 5, the answer has to be 7. That's what's going on underneath the hood, everyone. What's really happening, though, is you have an exponential and a logarithm canceling each other out. What you really have is you have a rule that says if you have a base, I don't know why I draw my box before I finish writing the formula. You get this. Base to log base b of m equals m. If I ask you, what is 3 to the log base 3 of 12 power, what's the answer, everyone? 12. If I ask you what's e to the log of 14 power, what's the answer?
14.
I have no idea what the answer is, because that's a base e and that's a base 10. That's right, Steve wins at the last minute. Haha, that's what you get for packing up early. All right, everyone, get out of here. I will see you on Thursday, and we will continue our discussion on logarithms. Stay awesome. Yeah.
I don't know if I missed this, but how do you get the number at the end of the now?
The little base on there?
Computer,
So on a computer, what you do is you just do a subscript.
like with a pre-work, because I got like 3 of them wrong.
Oh, well, there should be, in the pre-work, there should be
By taking the
a little
bar.
thing on the bottom that lets you put those in.
Man.
And if it's not there,
I feel like
if it's not there, try hitting Shift and hitting the underscore button on your computer, and that should push you down there.
Gotcha.
That should do it. So you type log and you want to put a 2 there desperately, and you can't do it. You hit Shift and the underscore button, and that should go in the subscript button.
Gotcha. And then the number next to it is just where it should be.
And the other one's just right where it should be. It's on the same level as log.
Gotcha. Awesome. Thank you.
You're welcome. Oh, people don't need to hear all this.